All right, let's get started. So, topic of today, we'll finish up our NC. Perhaps we'll do a little bit more of dealing with multiple clients, that sort of thing, and we'll also take a quick look at the email, assuming I can type in this weather. So, yeah. So just to review, let's take a quick look at what's going on with NC. And I don't know if I actually did this last time. I will. So what we want to implement is this nice functionality here. First, I'm starting up a server with -L. Maybe we need to look for those parameters too. So I'm starting up a server, and now with my other window here, I'll connect to that server, specifying the same port. And so now the two are connected. And what's really neat about this now is we have this situation here. The server is running here. It's got standard in coming in over here as well. So the server has two things coming in. And the client, same story there. This is actually a bidirectional link here. So this is what's going on with NC. And then both of them have output. They're also outputting whatever you type and whatever comes in on the socket connection out to standard out. Alright, so if I type something here, this is from the client, it shows up on the other end, and if I type from the server, here it shows up on that end. Okay, so that's a little small. So the difficulty that we encountered was that when we implement this thing on either end, if the client now wants to receive a message from the server, what does it do? Well, it waits on the socket connection. So it says receive on the socket connection, and then it'll just wait forever until the server has something to say. But if the user happens to type something on standard in, we're waiting on the socket, we're not going to be able to process that message. So we'll never send it over to the server, or at least not until the server sends something to us, so we wake up, and then maybe we can go fetch it. So one possible solution to that we discussed was to set a little option on the socket so that it doesn't wait. So it just, whenever you try to receive, it immediately returns. The problem with that is that then you end up spinning around and around. You keep looking all the time, and that without getting any work done. So that's quite wasteful and a dumb way to do it. Of course, you could put a little sleep in there. Right? So you don't have a hot loop, you just have a sleep loop. So you check, sleep, check, sleep. What do you think? Will that work?
That probably work. Still not the best solution.
So that's not the best solution. Why isn't it the best solution?
Because if we really care about latency, then you just have to wait.
Yeah, exactly. So you got this trade-off now. Now you have to decide, should I sleep for a long time or should I sleep for a short time? If you sleep for a long time, you'll have an efficient program. It's not going to use much CPU. But then whenever you type something, you have to wait for it to wake up before it sends something. So both options are no good. So select gives us a third option here, where we can wait for, with select, wait for multiple file descriptors at once. So now we're basically sleeping until something shows up either here or here, and that's where we left off. So let's get back to the program here. I should point out that there are a couple of other ways that we can deal with multiple inputs and not inputs in this case. For this situation, this is most likely the best solution, but we'll look also at using fork. If you have multiple clients, using fork could make sense. And we'll also look at using threads. So that kind of segues into our concurrent programming part, which is basically going to be the rest of the class.
So we have this problem and select fixes it, but how does select actually fix it? It's
Ah.
kind of one of these ways that we were talking about, right?
Very good question. No, it doesn't. So select is a system call. And the OS has a little more information than we do. So, and a little more liberty to do things as well. So what happens when you call select, the OS puts the process in two queues. There's a queue for this socket saying, so there's a queue associated with the socket, that's all. And then there's a queue associated with this file descriptor. So, and then we're in that queue, and then it just says, okay, I'm not going to run you anymore. So now nothing's running. Some other things are running, or maybe nothing's at all running for a while. And then when something comes in, over here or over here, the OS gets woken up by an interrupt. So it'll be either the network card interrupting because there's a packet that just came in, or it'll be maybe the keyboard interrupting because someone just typed a little bit on the keyboard. So that wakes up the OS. So it was already waiting for all these different events just by the fact that it has some interrupts enabled. So now it says, okay, it's from the keyboard. Let me see in the queue here who's waiting for the keyboard. Our application was waiting. Okay, so we go back and wake up that application. And of course, there's going to be a little bit more there because select actually tells us not only which one, but it says which ones. So you could potentially have stuff on more than one of these inputs, and it'll tell us for each one of them whether there's anything available for us. Okay, so going back to the code here. That's an excellent question, by the way. Okay, so we're creating our socket, we're binding it. I'm telling it to reuse the address, so that's so we don't get that little error message saying socket already in use. And then we're saying we're ready to start receiving connections. And finally, we wait to get a connection from a client. Okay, so far this is the same as any other socket server. Is this big enough? You back there? Yeah. Okay, so now it starts getting a little more tricky. So with select, you are supposed to pass it a set of file descriptors that you're interested in reading from, a set that you're interested in writing to, and a set that you're interested in hearing if there was any errors. So I'm not actually interested in any writing or errors. I'm just interested in reading, so I'm passing it in a read set. So there isn't, in C, there isn't set representation. Like in STL, you got this standard set, right? That's not how it works with system calls. Things tend to be very compact and bit flippy in nature. So here's a very bit flippy thing. An FD set is an array of integers, I think. I'm not sure how large it is. Maybe we should figure that out while we're at it. So I'll put it over here. Set is %b. Oh, read set. Okay, cool. So what we're saying here is, okay, I need a set. I'm initializing it all to 0, so there's no file descriptors in the set so far. And then I add one my client socket to the set. And then I add standard in to the set as well. Okay, so we have a set that includes client socket and the read set. And now I'm saying, okay, let's wait forever. If I don't specify a time over here, it'll wait forever. Let's see how we specify the time, actually. So it's a struct time val. A struct time val is two integers, its first number of seconds and then the number of microseconds, I think. So you can specify a wait for as long as you want there. Okay, so now select is waiting, and at some point select comes back. So how does it tell us that, well, what happened? The way it does that is it actually changes the values in its read set. So we pass in a read set with the ones we're interested in, and what comes back, so to speak, nothing really is returned, right? But this is then modified to only have bits set for the, or only have the members, let's say, that actually have something for us to read. So why do we care about that? Why do we need to know which one to read from now? We're done waiting. We can just go for it, right?
We might want to do something else for one case and then for something.
Yeah, so basically if we don't know, so here, let's see. So if I don't know if there's something to get from standard in, then I'll go and try to read from standard in, and again, it's going to wait forever. That's no good. So maybe a combination. One thing we could do here is we could say, ignore whatever comes out of here. We can have this non-blocking option set. So now we can try to read from standard in and see there's nothing there. Try to read from the next one, see there's nothing there. So on. Maybe a few dozen of these sockets. Try them all out. File descriptors, sorry. Try them all out, and then that will solve the problem. But now we're working extra hard again. Right? We're trying to read from all of these file descriptors. Every one of those reads is a system call. Bad idea. Much better to just check. This is a little bit flippy thing. Check if the standard in is part of the read set that resulted from the select call, and if so, there was some action in the standard in, and otherwise we try to read from the client socket. So this here seems to be perfectly general. We should go if fd is set client sock read set. Okay, so now we actually allow both. So we're saying, okay, there could be something on standard in, and later on there could be something on our socket. Right? That if else there, that's excluding. That says, okay, it can only be one or the other. Okay, let's see. Let's change this a little bit here. So we'll say also read in something. Yeah, but so we can't use buff because, or we use, it seems sloppy to use buff twice. So let's make another receive buff, standard in buff.
Actually, what happens when you have a declaration inside of the...
Oh, you mean what does it look like in the assembly? Or
Yeah.
So it's not inside of a loop in this case. Oh, you mean inside of this loop?
Yeah, it's inside of while loop.
Yeah, nothing really happens. Whenever you enter this basic block, the stack grows, and this is allocated in that part of the stack.
Just once.
Yeah. So every time you go around, the stack is the same size. Right? So we're all just reusing that element. I guess a benefit of that is you also get to keep the values, so there's nothing that the compiler needs to do, because it's always the same place, so the values are always going to remain. That might be helpful. Anyway, okay, so let's read something in. We'll say from 0 into standard in buff 2024. It's just like that, and then %s. Maybe we'll go okay, so I think we're not going to get I'm pretty sure we're not going to get a string terminator there. We're just reading from the standard in. The string doesn't really end when you're just reading. So we're going to have to end the string ourselves. So I'll put read len equals 0. Because otherwise printf will be upset. I'm using printf here. I could use write to standard out and just say this many bytes, and that would just work fine. But if we want to do it with printf, it needs to be a string, not just a bunch of characters. All right, let's try this out. Should go like that, maybe. What now? Oh, select. So I needed an underscore there. That's a strange thing to do. Okay, good. And we need. Oh, so you notice how I'm not getting any errors, even though I'm declaring stuff inside of here. I wonder if that's because I'm doing this on the Mac instead of on a Linux machine.
Why would you do errors?
I mean, you only use these things inside the if statement.
Yeah, but I didn't think that the standard C would allow me to declare local variables inside of here, but maybe it does. Maybe it's just inside of for loops I'm not allowed to do it. Anyway, we need to fix these pointers. 35, it's not pointers, it's errors. Where's 35? Ah, so this is a long unsigned int. So I'll say lu instead, and that should make it happy. Now, why do we get 2 errors for the same error? Beats me. All right, try this out. So now I think we can't actually type anything just yet. If I try typing something now, nothing happens. Any idea why?
We're not connected, so we're still waiting for the connection.
Exactly. Looking at this here, we're actually blocking at accept. So we're not in this select loop yet. All right, let's go a little further. So I'll connect with NC for now to port 8080. Ah, okay. There we go. So something happened. FTZ is 128 bytes. Okay, so we got a 128 byte bit array that is used now to represent our file descriptors. So how many possible file descriptors can we handle here? Speak up. What's that?
File descriptor is just a byte.
A file descriptor is it's a number. We usually treat them as ints.
32.
32 file descriptors.
We loaded 2 into them already. That's why it's 128.
No,
No?
no. So here, I'm saying how large is the read set? Read set here, this is just a type, just a C type. It has a fixed size of 128 bytes. So now, select needs a nice, efficient representation of this set, right? So what might be a good representation of which file descriptors belong to a set?
So they're ints.
File descriptors are ints, but you know what they look like. They're numbers. They start at 0 and they go up.
Single bit that says if it's 100 now.
Exactly. It's a bit array.
So 400 something.
400, he says.
Well, that's 128 bytes, right?
Yeah?
Oh, that's even more than that.
That's more than 400, yeah. 128 times 8. Yeah.
900 something.
Probably it's going to be 1024. If you think these are all powers of 2.
Oh, right.
Yeah. 900 something isn't really in that sense. But yeah, so 1024. 128 times 8, I bet you that's 1024. Okay, so we can handle, select can handle up to 1024 file descriptors. If we need more, it's not going to work out, I think. Actually, I'm not sure that that's quite how this works, so we can look it up maybe. But most likely 1024 is the limit on processes in this OS. You can only have 1024 file descriptors. That seems reasonable, but I'm not sure. Okay, so no, there's some more trick you can pull if you want more of them. I don't remember how you do it, but there's some more trick with select
What
that you
if
can
we
pull.
want we could just fork and then we could have 2 things waiting?
Yeah, but if you fork, then it gets very hard to coordinate after. So now you have 2 different processes, and how do they each know what the other one did? We'll see it a little later. That's not practical. Anyway, so now I'm saying, but I'm only interested in 32 here. That means select isn't going to have to spin through all 1024 bits to see if any one of those were set by me. Right? It's just going to look up to 32. So I could have said 4 as well. That would also have worked in this case. Okay, so what happened? It says something happened, and standard in says no. So we connected. I didn't type anything yet. right? So we went through here, and now select is waiting on both the socket and standard in, but standard in had something already. So then we go through, and it says something happened, because standard in happened, and that was standard in set now. Okay, good. So now if I type something over here, nothing happens. Any idea? We have this loop here. What's going on? Let's try one more time. I bet you it's going to work next time. So then maybe you can figure out what's going on. Okay, so now we're connected over here. It worked this time. Huh.
Can you type it again?
Can you do it on the actual
Yes,
server?
Oh. Huh.
It's only listening to one line.
Yeah. Okay, what happens if I type something here now? What do you think?
It goes all over.
Select modifies your read set, right? So would you have to reset the read set every time?
Exactly. So here's the problem. Select is changing this read set. We're passing in the same read set again. So now it's only listening to whatever happened last time. If we do it one more time. So now you see, okay, it worked. If I keep typing on the socket, that works. Now let's do it over here. So I say, oh, what?
Oh, that's that thing. We have to wait, right?
But yes,
Oh, yeah.
you
We should do that.
maybe OS has a minimum.
I think maybe my parameters I passed in here weren't quite right. Chances are. Maybe we should look that up. Let's see. Oh, that looks good. I like beach. Can we get an example, please? Set socket reuse adder. We have to have a value that's 1. Not val is an int. Okay, so we need a pointer to an int, and then we say it's 4 bytes. Okay, so let's do that. Of course, now we won't, and I already started that, but then I figured, okay, maybe we don't need it. So let's just do it. Size of. All right. Now, of course, we won't be able to tell if it worked because enough time has passed that we should be good. But maybe by the end of class we will know if it worked. Okay. So now if I type something more here. Oh, right. Gotta get connected. Now I can keep typing. Right. So the reason is, whatever I choose first, the very first time we go through here, the read set has both of them in it. Next time, when we have gone through this once, now the read set is whatever we saw last time. So we saw some action on the socket. That means the read set only has the socket in it, so next time we're only going to be listening for the socket. Or if we saw some action on the standard in, we'll only be listening for standard in. So we need to fix this. So I like to do it like this. No. I have a ready set and a read set. And I go fd copy my read set to my ready set. And I'll do that before every new run of this select. Okay, so let's see if the fd copy macro is available on this. It's not available everywhere. Yeah, it is. Okay. Okay, so what's going on now? So first I define my read set in the beginning. All right, that's now going to always be the same because I'm only passing in a copy of the read set to select. So now we have to check. We can't check the read set here. We have to check the ready set to see which ones are ready. but then at the very end, when I'm done processing the ready set, I put a new copy of the read set in there and back to select. All right, let's just check that I got the order of parameters right. FD copy, origin to copy. Okay, very good. Let's run that. Got connected. Okay. Okay, so we're almost there. Yep.
Why did that work if you're just copying the read set? Because if you just had the read set before, shouldn't it have worked the same way? Because you're just copying over the value again? If it's like you still change it the same way?
Yes, so select keeps changing the ready set. But if you look at the very end here, I'm now copying the read set. Select doesn't get to change the read set, it changes the ready set. So every time around the loop, the ready set becomes the read set again. And then select changes it again. So, yeah.
Seeing as FD copy is not on our Linux boxes that we have for AWS.
Oh, okay. Yeah, I'll supply the, actually I think I may have a, let's see if I can find the implementation. I had it somewhere. Ah, actually, it's not much of an implementation. We should all know how to do this. This is a C struct. Right? So how do we make a copy of this? I don't need to go this far. No, well, and that works, but we don't need to go quite that far either. It's a struct. I can just make an assignment. I think it should work just like this. So read set equals, no, other way. I know in C++ this works. I wonder with a C, I'm not sure about a C compiler, how that feels about it, but let's see. I mean, there must be a reason why there's an FD copy. But, so it used to be that you couldn't do these assignments. You could not make assignments between compound types. But feels like that ought to be in there now. It's such a convenient little feature. So let's see. Ah, look at that. See if it works too. Okay, good. Let's forget about this FD copy nonsense. So how does this work anyway? How did that work, this assignment? What kind of assembly do you think it translates to? What did I do with my window? There. Yeah, I just kind of disappeared. Yeah, so this assignment here. What does that translate to in assembly, you think? Just a move L. Wait, is it called move L? Oh, okay, yeah. Yeah, move L or move Q on your 64-bit machine, but that's only going to move 8 bytes. Doesn't seem enough. We have 128 bytes here to deal with.
I just figured that just point at it.
Point at it. No, we need to do, has to be assignment by value here. We need to get a full copy of everything. Any other thoughts?
I mean, I guess we know like what this struct looks like.
Do we care?
Because usually in a struct there's more than one element. Right?
Yeah.
Okay.
So we know it's 128 bytes. We do not care what's in those 128 bytes. We just want to make sure we have the same ones at the other end. Let's look at it. I mean, networking is fun and all, but this stuff is better. Let's take a look. Oh, we're on the wrong machine here. Let's see. I don't have a this O tool. Is there a disassemble? Maybe we can't do it because I don't know how to do this on the Mac.
Right there at the bottom.
You see it? Oh, Q. Oh, Okay. Print disassembled. No, we gotta disassemble something rather. Print the text section. Ah, TV. Okay. TV. And what was it called? Select server. What? Okay, well, fine. I don't care. I know how to do it in here. And what was it called? This is just the main, right? Okay. I need this to be a little closer to me. Let's see if we can figure out where it is. I like this stuff, so. Maybe it'll be better if we have this with debug headers. Let's just do that.
Is it a lot of move statements?
Yeah, probably.
Yes, that
Yeah, I was thinking we would get. Oh, that looks suspicious. Oh, no, that's no good.
That's where it's clearing up.
Yeah.
Looks like it's
That's the FD clear, so it's going to be a little further down. Okay, but that's the clear. Okay, so now we should be pretty close. Where are we doing the copy? So we got a couple of sets. A 0. This got to be the 0. Right, there's no other. Okay, a couple of sets, and then we're doing the assignment. So how bad can it be? Huh.
It leaves an address in
Here.
PDX.
That's the one. So, you know, there's many of these assignments that need to be made. So it could either be like this, or it's got to have to be a loop, right? So in this case, it looks like we're sticking, here's the value from the stack into RSI. We need to know how long, probably in this in here, it's probably the number of steps. This didn't get as exciting as I had hoped. It would have been much more fun if it was like this. Anyway, so you see, that's basically what it expands to. It's just going to copy the stuff over, and it doesn't care what's inside.
Is there any reason why one is has each one individually and the other one is a loop? Like, how does it decide?
I think these. Oh, yeah. Okay, so if I did FD copy, it would probably do something different. So FD, this is probably implemented in assembly directly. Or at least it does something that's different from this assignment. Like in terms of of how it's written. Let's do one more thing then while we're at it. Oh, now we got 2 GDBs together. That's maybe not what we want. Okay, what is that? Okay, fine. GDB disassemble main. All right, let's see. Huh, no, looks quite similar. Oh, look. Yeah, now it's doing a bulk copy there instead. From some, ooh, that looks really inefficient.
then if you compare with like O2, do you think it changes this?
I don't think the compiler can do anything about a function call. Well, it could inline the function call.
Actually, the assignments. Maybe then figure out the assignment.
Oh, with the assignment, yeah, that's true. Okay, so, okay, fine, we'll do one more try here. So, to see if it does something really clever if we do with optimization. It's fun.
Is it true that if you do O2 or above, that actually it
I have no idea. All right, one more. Whoa, look at that. Move APS. Yeah, so it definitely did things different. This here is that multimedia extension stuff, SSI or whatever it's called,
Is that a
SSE.
floating point register?
Yeah, but you know, it's not going to be doing floating point in here. They actually share between the SSE implementation. It uses the same registers as the floating point processor. I don't know why. I guess it's, wow. Okay, so look. So this looks like, first we're clearing out a very large register. These are probably, right, we need 128 bytes. And so we have 8 in each. So we need, what's that then? 128 by 8. That's 16. And this is only 8 of them. So we get 64. If we were doing moves with 64-byte registers, we would only get, with 8-byte registers, 64-bit registers, we'd only get 64 bytes. But here we're doing 8 moves and we're getting 128 bytes. So these must be 128-byte wide registers. So what it's doing is first clearing out the register and then moving the contents of that register over to various offsets into the stack. So that's the same clear here. And now the copy is quite different. Right? Now the copy is actually doing the right thing here. So we're moving something from our previous, this is from the read set, right? Same offset. From the read set to XMM0, then from XMM0 to, and this got to be the ready set. We're doing that 8 times. Actually, we're not doing it 8 times. Look, it changed its mind midway. The first 4 we'll do through XMM0, and then, okay, we'll just use the other registers.
Probably pipe optimization.
Yeah, could be. Could be a pipeline optimization sort of thing.
But why didn't it do it for the first 4?
It's probably in blocking issues.
No idea. I mean, the compilers move in mysterious ways. But anyway, we have an idea of what's going on behind the scenes. That's the whole idea of the class, after all. So, good. Where are we? Oh yeah, we're gonna let's forget about if something happened here. We don't need this FD copy nonsense anymore. Oh, wrong one. Surprisingly hard to know which line you're at when the display is kind of at an angle. Okay, so, but we're not quite done here, right? Because if we type something here, we want to get it sent to the other end, not print it out. So why don't we do that? So we'll say write client sock standard in buff and then readlen. So I write everything that I got. Forget about this. This one is already writing things out on standard out. So I think we're in pretty good shape there. And then if we have time, we'll do 2 clients coming in. Okay, so our select server. Let's talk to it. Hello there. Ah. Okay. So we're in pretty good shape. I wanted to see if NC actually supports multiple incoming clients. Because that would be a nice little feature. So let's try this. So I've got one talking to it, and I'm going to try another one here. Huh. Just the one.
Code actually. Don't need this to make sense once.
So the server here, so far, is only paying attention to the first client. Now let's quit the first client and see what happens. Huh. So NC doesn't like to be a proper server. It seems to only want to do one session, so to speak. So if we wanted this to work, now this one here, it was waiting. It was hoping to get a connection, right? Because that port was bound. And NC had said, I'm listening. So the OS was buffering this connection in the hopes that NC will come back and try to accept the next connection, but it didn't. So we can do that. We're the server, right? So let's just try to handle that. So let's see. So now we have something here, and now what if we try to read but we get nothing? If it's bigger than 0, then we write it out. Otherwise, we'll close our socket. It's actually probably already closed, but because we didn't get something, that's because the client closed on their end. But will be nice. Okay, and then try to get another one. Oh, what happened? Client socket. Oh, no one there. We're 80-80. Okay, do another one. Small. Okay. Okay, so both of them seem to be happy. Happy? Yes. Okay, so now we'll close this one. Oh, that quit. I didn't get any output here. I forgot to put a print statement, but let's see. Oh, it's not happy. What happened? I should have put a print statement here. If readlen is, so we closed it. This really ought to have worked. Okay, let's see if we actually got a close here.
Can you type something in the server?
I mean, now I quit this. So I closed the program. It ought to have closed this socket. Let's see, am I looking at the right one here? Oh!
We're doing standard in.
I'm trying it on standard in. Okay, that was not the most clever move here. Let's try it. Let's see, what am I even looking at here? Okay. So we want to know if we read. So if we close standard in, that doesn't seem very interesting even. So we'll just put all of it here. What do I do? There. Okay. Good, else write it out. All right. And I don't really need to redo the mem set because this didn't read anything, so we're good. All right, let's try this out. I guess this can stay because there's no point in trying to write something if there wasn't anything actually received from standard in. So that's good. Connect. Connect. Hello. Huh, no answer there. Why? Because it's connected to the other one, yeah. There's the other one. Let's close this one. Now we got the hello. close this one. Oh, now they're both closed. We can connect again. Okay, so we're pretty good. But it's not really where we'd want to go, right? Because we can only talk to one client at a time. Wouldn't it be better if we can talk to both of them at a time? All right, that'd be a much nicer chat client here. Or so what? Party line. Yeah, exactly. Okay, so let's try that next. So now that becomes sort of a different thing here, because now we want to see, oh, if the server socket says there's anything to pick up, right? So if the server says, I have you can't really read from a server socket, but you can accept from a server socket. So that ends up being in the read set as well. So I'll say fd set server sock read set. So now we're listening for the server sock as well. And then we'll say, instead of this stuff, I'll just remove that. I'll say if fd is set server sock. Okay. Skip this stuff and we'll just, oh, that's a tricky one. That's a tricky one because client sock, that's maybe now an ongoing socket, so we can't go throwing that away. So we'll have to count how many clients we're talking to. While we're at it, why don't we skip doing the accept up here. So now in the beginning, we don't add a client sock. So now we're just waiting for the server to say it has something coming in. And then we'll have, let's see, a bunch of clients. Up to 100 clients. Okay, so when the server says I got something, we'll have to say clients, what's it, client FDs?
Yes.
Client count equals accept. So now we're getting something in here, and then we'll have to add it. FD set client FDs client count to the read set. All right, and then we have to increase the client count. And then finally, this is going to be a little bit of a mess too, because now we have multiple clients. So we'll have to say for C0, C less than client count. So we have to check for every one of these clients. Do we have something coming in? So it'll be client FDs. Hello. Ah. Running against the clock here, you know. Okay, so now we're checking all the clients. And we're just increasing our count whenever we see something. Okay, it looks pretty promising, and we only have a minute to go here. I better compile this, and it's a Hail Mary kind of thing. It's just come on.
Try combining GNU because it's
No, it's upset about the client sock.
some spots.
Oh yeah. So now I have to write to all of them if I want this part to work. Maybe we can just skip that. Nah, I'm gonna have to finish this next time.
So close.
So now if we wanted to do it this way, we wouldn't be able to close file descriptors.
Well, we're using up ints in our client FDs, but the rest works. So we have a bunch of extra of those file descriptors, but yeah, it doesn't really matter. We're not really wasting it. Except at some point we reach 100, and then we can't accept more clients.
So we could just run it into, say you could decrement client count every time someone closes, but then you have to get their
Yeah, so it's like malloc then.
Right.
Like, how do you find the free one out of these?
Yeah,
Okay, I'll see you next week.